Hello students, in this video we'll define the Fourier transform and discuss several properties. So we're going to discuss the Fourier transform. Okay, and that's if for f mapping R into R. For just real valued functions we can do this, you can do it for complex valued functions as well. Define f hat of xc is the integral from negative infinity to infinity of the function f of x e to the negative 2 pi I x xc dx. Now, of course, this integral has to exist, so this will exist, for example, the function f is in L1, for example, if it's absolutely integrable, okay? So in other words, we're going to consider functions, and if f is sufficiently smooth of a Schwartz class, we know this will exist, okay? So these integrals exist for well-defined, sort of regular enough functions, okay? And so what are some properties of this Fourier transform? So the first properties, so what are the elementary properties of the Fourier transform? Properties. The Fourier transform is linear, right? In other words, if I have f plus g hat of xc, this is f hat of xc plus g hat of xc, and lambda f Fourier transform of xc is lambda f hat of xc, right? In other words, that's clear but just by the linearity of the integral. So this is linearity, so the Fourier transform is a linear operator, linearity, okay? That's the first property. Now let's talk about modulation. So how does the Fourier transform work with modulation, okay? So here's the modulation properties, right? So modulation, okay? Now what do I mean by that? So let me do the following. I'm going to, if I translate the function f, right? So if I look at f of x plus h, if I look at f of x plus h, I translate the function, and I Fourier transform or translate the function, that's the integral over r. I'm just going to over r from negative infinity to infinity of f of x plus h e to the minus 2 pi I x dot xc, x times xc. Now, of course, what we can do is we can make a substitution over here, right? What we're going to do is we're going to let y be x plus h. Then x is really y minus h, right? So this becomes what? This becomes the integral over r, that my limits don't change, of f of y, and then e to the minus 2 pi I, and then we have x, but x is really what, according to this? X is really y minus h. Y minus h, xc, dy, beautiful. And of course, what do we have over here? So this is really just the Fourier transform of f, and then what is the extra factor? This is just e to the 2 pi I, and then we have an h xc, f hat of xc. So in other words, if I translate the function, that modulates the function over here by this e to the 2 pi I h xc. Okay, great. And then what's left over is just the Fourier transform. Excellent. Now, conversely, what happens if we modulate the function by this factor over here? Well, that do the Fourier transform. So conversely, if I look at e to the 2 pi I h xc hx over here. So there's my modulation on the space side. Remember, the space side is x over here. So that's another good thing to know. We call x the sort of the spatial variable, and we call xc the frequency variable. Okay, great. F of x, if we Fourier transform this thing over here, what's going to happen? Well, it's going to be the integral over r of f of x e to the 2 pi I x times h, then e to the minus 2 pi I x xc. Okay? And so this is just going to give me a what? This is going to be this whole thing over here, dx of course, is just going to be the integral over r of f of x e to the what? E to the 2 pi I x, and then with a minus sign, and then we have a minus xc minus h. So this is just the Fourier transform shifted over by h units. So this is, of course, just f hat of xc minus h. Great. All right. What are the next properties of the transform? So those are the modulation properties. Let's talk about the differentiation properties. These are the most important ones over here. So differentiation. How does the Fourier transform work with differentiation? Okay. In other words, if I have the derivative, if I have f prime of x, and I transform the derivative, that's going to be the integral over r of f prime of x e to the minus 2 pi I x xc dx. Now we'll integrate this by parts over here. So this is going to be my dv That's going to be my u. So I'm going to have what? I'm going to have v times u. So that's going to be f of x e to the minus 2 pi I x c over r. And then minus the integral over r of v, and then du. So that's going to give me a what? I'm going to bring that factor down. So minus 2 pi I what? Doing the 2 pi I x c, and then e to the minus 2 pi I x c x dx. Great. Okay. Now, I have to assume the function f is decaying sufficiently rapidly at infinity for this definition to make sense, so those terms have to be 0 by the decay at infinity. And so we see exactly what we see now, that this has to be equal to, that this is equal to what? I have a minus over here, and a minus, that's a plus, so this is going to be equal to what? So hence, f prime hat of xc is 2 pi I xc times f hat of xc. And so in particular, what this tells me is that if I do any number of derivatives, if the function is sufficiently regular, if I do k derivatives, for example, hat of xc, that this is going to be 2 pi I xc to the power k, f hat of xc, right? In a special case of this happens when k is equal to 2. When k is equal to 2, what's going to happen? I'm going to have a 4 pi squared negative 1 xc squared, right? So that's a very, we're going to see that in applications like the heat equation and the Laplace equation, okay? Excellent. And then what's the last property we'll discuss? The last property we have that we're going to discuss with differentiation is that if we do the derivative of the Fourier transform, so I do d by dxc of f hat of xc, that's d by xc of the integral over r of f of x e to the minus 2 pi I x xc dx. And so if we bring this xc derivative inside here, I'm going to have a what? I'm going to have a 2 pi I x that comes out, right? So in other words, this is equal to the integral over r of negative 2 pi I x f of x e to the minus 2 pi I x xc dx. And so that says the Fourier transform, if I Fourier transform what? The Fourier transform of negative 2 pi I x f of x will transform, Fourier transform, just to d by dxc of f hat of xc like that. Thank you very much.